Hey guys, so in this video I'm just gonna go through last year's electricity paper. So yeah, let's get to it. Okay, question one, capacitors. Kate is learning about capacitors. She investigates a capacitor found in a camera and it's labeled at 185 nanofarads. So that's our capacitance there, and it's got a 1.5 volt battery. Show that the energy stored by the capacitor when it's fully charged is this number here. So the energy stored in capacitor is half of the energy supplied, right? Which is half QV, right? And we also know that Q equals CV. So substituting Q equals CV into here, we get half CV squared. And then now we can substitute our numbers. So a half and then 1.85 times 10 minus 7 and 1.5 volts, and that gives me, I get 2.08125 times 10 to the minus 7 joules, which is 2.08 joules to three significant figures. Sorry, 2.08 times 10 to the minus 7 joules. Okay. The diagram below shows the circuit used to charge the capacitor. It's got an internal resistance of 0.27 ohms, um, 1.5 volts, and the 185 nanofarad capacitor. Sketch a curve by plotting at least 4 points on the grid opposite to show how the charge on the capacitor plates varies with time once the switch is closed. So once the switch is closed, we know that a capacitor will start to charge, right? Therefore, um, with time, it will approach the total charge accumulating on the capacitor will increase. So the time constant. Okay, so for the time constant, we know that for a RC circuit, T is just RC, which will just be 0.27 times 1.85 E oops, times 10 times 10 minus 7, which is, that's, so I get 4.995, but I'm just gonna write 5 times 10 to the minus 8 seconds. Um, okay, so we've got the time constant, that's done, and the maximum charge. And our maximum charge, Q max, will just be the capacitance times the maximum voltage, right? And that would just be 1.85 times 10 minus 7 times 1.5 volts. That's a maximum voltage. Sorry, excuse me. Okay, so putting this in my calculator, 1.85 E minus 7 and 1.5, I get the maximum, our maximum charge to be 2.78 times 10 to the minus 7 coulombs. So, okay, all right. So we got that. Cool. Now we have to sketch the graph. Okay, so. Alright, now we gotta work it out. So we know that because it's exponentially increasing, our graph will take this form here, that our charge after a certain number of time constants will just be our maximum charge times 1 minus e to the negative time constant, like how many number of time constants. And so that means for after one time constant, our charge on the capacitor plate will be, what? Oh, we have to change it to times 10 minus 8. So move the decimal the other side. So then we'll get 27.8 times 10 to the minus 8 coulombs. And now they're the same. Okay, so 27.8 27.8 times 10 minus 8, 1 minus e to the negative 1. Putting that in my calculator gives me uh, and I get 17.6 times 10 to the minus 8 coulombs. And then after two time constants, it will be q max times 1 minus e to the minus 2, which is just going to be uh, 24 times 10 to the minus 8 coulombs, and then q3. How many did they want us to do? At least 4. Okay, at least 4 points. Okay. So after three time constants, it'll just be same thing, qm bracket 1 minus e to the minus 3, and that gives me 26.4 times 10 to the minus 8 coulombs, and then at q4 I get minus 4, which is uh 27.3 times 10 to the minus 8 coulombs. That's pretty close to our maximum charge, 27.8, yeah. Okay, so let's start plotting it up. So one time constant, after one time constant, it's 17.6. Let me just see what's the scale interval for this. 2, 4, 6, 8, 10. Okay, so 17.6 would be just around here, I'd say. And then after two time constants, it is 24, so that is here. After three time constants, it's 26.4, so probably right around there. And after four time constants, it is at 27.3, so that would be right around there. And so our graph sort of like takes this nice little exponential shape. Let's hope I draw. Okay, that's bad. Hold on. Wait. Okay. All right. There we go. That looks all right. Yep. So that's that one. Sketch a curve and yep. All right. Next one is a capacitor one. So we've got two metal rectangles. Okay. So using our capacitor construction formula, C equals E0 ER A on D, we are asked to find the distance between the rectangles. Therefore, we get that D is equal to E0 ER A on the total capacitance. And that's just going to be our primitive free space is 8.85 times 10 to the minus 12 times 2.1 times 3 3 point, oh my god, area is just base times height, so 3.2 times 10 minus 2 by 1.83, all divided by the total capacitance, which is 1.85 times 10 minus 7. And that gives me a distance of I get 5.8829 times 10 to the minus 6 meters. It's quite close. Or 5.88 times 10 minus 6 meters to three significant figures. Okay, so that's the first question done. Oh no, not yet, not yet, not yet. All right. Question D. So the charge capacitor can be discharged through the lamp by pressing a switch in the camera. And okay, you should show. Okay, how it compares. Okay. Okay. So let's just see, like 200 volts divided by 1.5 equals, okay, that's is about 133 times larger, right? So, okay, so as E equals a half CV squared, and now the voltage is 400 on 3, that's 403, isn't it? Yeah. As energy is now 403 times larger, we can just go half C times 400 on 3 squared larger. So energy will be, and then that squared is about, geez, 17,000. Energy, this means that the total energy stored will be 400 on 3 squared times larger, or that is 17,800 times bigger. Okay, so that's that bit. So we've compared the energy stored. Alright, now this higher voltage increases the initial current from the capacitor when it is connected to the bulb. So as V equals IR, basically, okay. Yeah. So as V equals IR, where R is constant, and an increase in the voltage will result in a proportional increase in the current initial. Okay, so we've got this one and increase the initial when it's, yep. And then for this one and for the third bullet point, as P equals I squared R, where um where R is constant, since the current has increased, so will the power output by effect of current squared. So um in watts. So yeah, that's about that one. And so we can just write a little statement like, therefore, this arrangement allows for a much more powerful flash. Boom. Okay, nice. That's the first question done. Sweet. So Kate School has a demonstration transformer printed alongside. Okay, so I don't really have any picture here, but picture to the main supply. Okay. Okay, so for this one, we can just use the relationship that NP over NS is equal to VP on VS, right? And we have NP and we have VP and we have NS, so we have to find VS. Um, Therefore, with this, we can just write that if we just times that to both sides, so if we go just times VS times VS, and then if we just times by NS on NP, then this and this will cancel out, and this will cancel out, and so we will be left with VS equals these will cancel out, so VP times our number of secondary turns divided by our number of primary turns, and that just gives me that VP was 240, and our secondary coil is 600 turns, and divided by 12,000, which is 12 volts. Okay, so the two coils are held by a ring of laminated soft iron which runs through the core of each coil. Explain why an AC voltage uh, okay will produce a okay, so this is like a mutual inductance question. Um right. So basically, right, because this is alternating current, the changing current produces the changing current in the primary, I should write, in the primary coil produces a changing flux, a changing flux within the coil, right? Wait, is this okay, not yet, right? Okay, all right. Produce a changing flux within the coil. And basically, when the secondary, when the secondary is close enough, close the an AC edge be produced. An AC voltage will be produced in the secondary. And the secondary. This is and then we can just write that it's based on Faraday's law. That our back EMF will be negative d phi. Oops. Negative d phi on dt. And so basically this changing, so what we've got here, this changing current, right, will the equation that shows the changing current is this one, right? We know that E equals negative L times di on dt, right? And so basically, both of them are EMF. So if we just go set them equal to each other, then you'll notice that negative d phi by dt is equal to negative L times di by dt. And we can just cancel the negatives and the dt, and we see that d phi is equal to L times di, right? And so basically this changing current or di would also is a result of the changing flux, right? They're both like they complement one each other, right? So if you have a changing current, you'll have a changing flux. And then if you integrate both sides, then you just get phi equals Li, but yeah. So that's that one there. Um, is there anything else we need to cover? No, not really. And basically for this one, the coils are wrapped around ring to improve flux transmissions. So that's basically that one. Yeah, so it just improves basically the iron ring just like improves the general efficiency, like less of that flux would be lost to the surrounding, and yeah, so that's the whole point behind that one. Okay, so Kate connects the 12,000 turn primary coil. Alright, the coils are still linked with iron. Explain why the Okay, so basically, right? Okay, so for this one, it's like when the switch is closed, when the switch is closed, um, so the current will start to rise, right? The current will rise from I to I max, right? Yeah. So basically, this means that obviously the change in current is greater than zero, right? There is a change in current that exists. So um, this uh, this changing current, this changing current um, will produce an EMF in the opposite direction to resist the change. And this is according to this equation here, negative L times di by dt, right? Um, wait, but in the formula sheet, they just use okay, they use delta. All right, so in other words, like delta t, right? And because delta I is greater than zero, right? And that means that because of this negative sign, the EMF will basically be negative, but the negative is just direction, right? It will oppose the changing current. So this term will be positive, and a positive and a negative will make a negative on this side. Therefore, like there'll be a back EMF. And basically, so you got like this current going in this direction, right? But then you're gonna have this back EMF um um in this direction, and that will cause the net current remaining to be a bit smaller, right? And so basically, therefore, it will take current um, slightly longer to uh, to reach I max and so that's why it comes on after a slight delay. Okay, so the power station that supplies Kate's area generates 50 kilowatts of power, and voltage is 220 kilovolts. and the resistance of the transmission line is 4 ohms for every kilometer. So we know that the power is equal to 50 kilowatts, and our voltage is equal to 220 kilovolts. Um, to calculate the power lost as heat energy across a distance of 300 kilometers. Okay, so let's work out the current. We know that P equals IV, so I is equal to P on V, which will just be 50 kilowatts on 220 kilovolts, and we're just gonna get 5 on 22 amps, which is um 0.227 amps. Okay, and now we can just use the equation. The power lost to heat energy is I squared R, and so I'm gonna, in my calculator, I'm just gonna use like the full decimal place, so 5 over 22. So this would just become like 5 over 22 squared times the resistance, which is, so 4 times 300, right? And that gives me 5 over 22 squared 4 by 300. And I get 61.98 watts. So therefore 61.98 watts is lost to heat, uh, is lost to the surroundings. Okay. Comment whether this amount calculated is significant to compared to a situation where voltage is transmitted at 25 kilowatts. Okay, so if assuming the power is still 50 kilowatts, with our voltage now being 25 kilowatts, we just get the current is just 50 on 25, which is 2.0 amps, right? And so P equals I squared R, which is just going to be 4 times 4 times 300, which is just 4,800 watts. And basically, if we just go, okay, 4,800 over 61.98. This is 77.44 times more power lost to the environment, and so this amount is significant compared to like if the power was just transmitted at, no, sorry, the voltage was at 220 kilovolts. So yeah, that's that one. Okay, question 3. Okay, AC. Okay. Um, 200 hertz. So this is, show that capacitor. Okay, so we know that for a capacitor, it's inversely proportional to frequency, so 1 on omega C, which is 1 on 2 pi times F, which is 200. And R equals 15 ohms. and their capacitance is 1.2 times 10 to the minus 6 farads. 200, 1 on omega, which is 2 pi f times 1.2 times 10 minus 6, and putting that in my calculator, I get 663.1455 ohms, which is 663 ohms to three significant figures. K increases the frequency of the signal generator from 200 hertz to 20 kilohertz, and then 200 kilohertz, 20 kilohertz to 200 kilohertz. Okay. Oops. Given an in-depth explanation of what Kate will observe in the circuit at each frequency compared to her observation in part A, consider the effect of changing the frequency on the impedance, the current, and the brightness. Okay, I'm just gonna create a little diagram to just show exactly how this goes, but basically 200 hertz, and then 20 kilohertz, and then 200 kilohertz. And we're just gonna go impedance, so Z, and then our current I, and then our brightness, we'll just go B. So basically, okay, that's so bad. Hold on. So there's just some small little fundamental equations we should know, such as V equals I Z, and Z equals the square root of your we don't have an yeah, we just have a capacitor, no inductor. So we would just go resistance squared plus your capacitive reactance squared, and that basically your capacitive oh, the reactance of the capacitor is inversely proportional to the frequency. And so as the frequency increases, we know that the capacitive reactance decreases, and since Z is proportional to XC, a decrease in XC will result in a decrease in Z. And as Z decreases, that means your current must increase as V is constant, right? So in this case, it's just this is all initial, right? This is all our initial observations, because that's what the initial thing was, the frequency was at, right? 200 hertz. So initial and then initial, right? Whatever that was. And then since the impedance decreases, right? So Z will decrease a little bit, and so our therefore our current will increase, and so therefore our brightness will also increase, right? And then um And then as we increase the frequency more, then our impedance will decrease a lot more, and our current will increase even more, and so our brightness will increase more. And basically, you don't really have to do this in the actual exam. You should probably just put it into words, but um, like basically as she increases the frequency, the bulb will continue to get brighter because you're decreasing the total reactance. So basically your total reactance in this case is just equal to the capacitive reactance. And so yeah, that's that one. um, so yeah, it would be much brighter. uh, Yeah, so make sure you just like put this into words, give it as a worded answer. Um, Kate adds a 0.2 Henry inductor in series with the capacitor, and it's set at 2000 hertz. Decreases the frequency. The lamp suddenly grows brightly but goes off at lower frequencies. Okay, so if we drew like um an impedance phasor diagram, we'll see XL, XC, and then we'll have our current, right? Our circuit current, and basically the graph sort of like looks somewhat like this. And basically we're trying to find this maximum point here, right? When the that's your this is a graph of your current um as based on the total reactance, right? And so what you see here is that current is at a maximum when XL equals XC, right? So at the origin, right, that's just 0, 0. So therefore, when XL equals XC, right, or the difference between them is 0, right, that's when your current will be at maximum. This is also called like resonance or your resonant frequency, and that's given by this formula here, F naught equals 1 on 2 pi root LC. And this is like the starting base on how to prove it. Um, I if you want, I think I'll just go through it. I'll show you. So basically, we know that XL is equal to omega L and XC is equal to 1 on omega C, right? And so we get omega squared is equal to 1 on LC. We're trying to find F, right? And so omega is equal to 1 on the square root of LC. And so going up here, so then we get 2 pi times your resonant frequency is equal to 1 on the square root LC. And so dividing by 2 pi, we get F naught equals 1 on 2 pi root LC. And let's just plug in the numbers. So 1 on 2 pi times the square root of 0.2 times, oh, what is our, okay, 1.2 times 10 minus 6 times 1.2 times 10 minus 6. And that just gives me, and I get 324.874 hertz, um, which is basically 325 hertz to three significant figures. Um, okay. All right. So question D. Um, explain how explain how the inductor affects the impedance of the circuit and why there's one frequency at which the impedance equals to the resistance of the circuit, which is 15 ohms, causing the lamp to go brightly. Okay, so basically, if we go back to the phasor diagram, right? So we notice this component here is XL, and that leads by 90 degrees, right? And this component here will be XC, which lags by 90 degrees, right? And basically, what it is that XL and XC are directly opposite each other, right? Which means that the two vectors can cancel each other out, right? And totally they can totally cancel each other out, right? So XL and XC are um they're basically out of phase. and they are inverse to each other, um, and basically when they're inverse to each other, they can cancel each other uh, and are inverse to each other, um, and they can cancel out when the two vectors are equal, um, then they can cancel out. When the two vectors are equal, they entirely cancel, and so um, xl minus xc equals 0. And if we go back to our equation, z equals the square root r squared plus your total capacitance squared, you'll notice that that total capacitance is 0. So you just get z is equal to r squared plus 0, which the square and the square root cancel out. And so you get z equals r. And then you're just left with, if you go back to v equals iz, which is just I, oh, which is IR. And no more impedance in the circuit. And since impedance is at a minimum, right, which is R, and your current will be at a local maximum. Um, and basically explain how the inductor affects the impedance of the circuit and why there's one frequency, they entirely cancel out. So now the size of each vector, and we should just mention that the size of each vector is um, is proportional to the frequency, right? Um, and that's just XL equals, we can write that XL is just proportional to the frequency times the inductance, and XC is proportional to 1 over the frequency times the capacitance. So basically, if you increase the frequency, right, in both equations, then you'll notice your XL increases, but your XC decreases, right? So basically, that's, yeah. And so this component will get further that way, and this component will just keep coming down. So and eventually, once they're equal, then they'll just cancel out, and so there will be no more reactance within the circuit. But yeah, pretty much. Yeah, that I mean, you could probably phrase this a bit better, but yeah, this is just like a rough overview. But yeah, that's the 2023 electricity paper done. Yeah, thanks.